Okay, so I'm happy to talk about this paper today. This paper was accepted 2 days ago, so I'm very happy. I haven't even put it on Ashpage yet. So first I want to thank my collaborators. This work is a collaboration of many people, including some sitting in this room. And I will talk about the new near-infrared luminosity function from AKARI telescope, but this time using all of the AKARI NAP field data as I introduced. So the scientific motivation is when and where stars are born in a long history of the universe. So we want to review the cosmic star formation history. That's our scientific motivation. But as you all probably know, that if you use ground-based telescope and UV optical light, you suffer from extinction. So that's a problem. So how do we measure obscure star formation? Then our answer is AKARI Space Infrared Telescope. That's why we built a telescope, put it on space. So this is the launch movie. Turn on the volume. So then AKARI did this in some synchronous orbit. So it did also a survey. But in addition to that, in this region AKARI look at it every day. So we have a deep field here. So that's the data we are going to talk about today. And then so this is a deep field data in the North Equatorial region. This is mid-infrared, has 9 bands. Okay, so it was supposed to be this way. So AKARI, the unique feature of AKARI is it has 9 continuous filters in mid-infrared. So from 2 micron to 24 micron, there's no gap. It's all covered continuously. This is in contrast to Spitzer or White. In case of Spitzer, there's a large gap here, right? So if your feature is in between these bands, in case of Spitzer, then there's no way to recover it. But in AKARI, one of the filters can capture the feature anywhere in mid-infrared. So that's the nice feature. And AKARI is the only satellite which has continuous mid-infrared coverage until JWST goes up, which hasn't happened yet, right? Then we used this data previously, and then wrote a paper about cosmic star formation history. This is the cosmic star formation rate density as a function of redshift gradually going up. But this previous work had a problem. This was only using part of the AKARI data. What I mean is, so this is the AKARI data. This was reduced by Kim. He's the next speaker in this session. This is 5.4 square degrees. It's a very large area. But our previous work was only using this 0.25 square degree area because this is we had only deep data, deep optical data we only had in this region. This is the one field of view of the Suprime-Cam, so which is not a small field, but 5.4 square degree was just too big to cover with 8-meter telescope. So that's why we suffered from, our measurement suffered from cosmic variance. The situation changed with the new Supreme Hyper Suprime-Cam. So this is the new Supreme Hyper Suprime-Cam, which has 0.75 degree point of view. This is my student having fun in Hawaii. And then with using this Supreme Hyper Suprime-Cam, we covered the whole 5.4 square degrees with the deep optical coverage. So now we can finally use the whole AKARI NAP field data. That's the new point in this paper. Okay, so the area is 20 times larger than our previous work, so we don't suffer cosmic variance anymore. And then a lot of young people worked hard to obtain data and then reduce data, including some at NTHU. And then so now this is the HSC data, new optical data covering whole 5.4 square degrees. And as you can see, this is a power of 8-meter telescope. G-band depth is 27.5, so that's nice, right? So we can detect faint, very extinct optical sources. Okay, and then the problem of HSC is it doesn't have U-band capability, but our graduate students at NTH Kevin has reduced the CFHD U-band data. CFHD we have access to Academia Sinica. Thank you. So now we can do photology, and then Nagisa calculated photology, and it's very accurate. The 1 plus D dispersion is 0.036. So now we have photology for all of the AKARI's infrared sources. Okay, so now we're ready to do the science. So we cross-match with AKARI's infrared sources, and then we have photology, so we know distance, then we know the luminosity, and then using Bmax for the correction for luminosity, and then we can draw luminosity function. Now I first saw the result of the 8 micron luminosity function. 8 micron is this area dominated by PAH emission, which is sensitive indicator of star formation activity. So we can the census of star formation activity. That's good. So then, because of the continuous filter coverage, whatever redshift your 8 micron feature is, one of the filter covers directly 8 micron feature. So if galaxies are redshift 1, it's just 50 micron filter. If redshift 2, it's 24 micron filter. So that's very nice. This is very different from Spitzer, where you have to extrapolate from 8 micron and 24 micron. So our estimate will be more accurate than Spitzer. Okay, then this is the result. And then you see a very nice smooth evolution from redshift 0.4, 0.8, redshift 1, and then redshift 2. Okay, very nice smooth luminosity evolution. Okay, then 12 micron luminosity function I'll skip, and then I'll show one more result, total infrared luminosity function. So total infrared luminosity function, we still need to do the SED fitting because we don't have the longer wavelengths all the way. But having 9 data points around here still helps. In Spitzer or White, you only have 4 data points, but we have 9 here, so that you can do it. We do it more accurately. This is the result in total infrared luminosity function. Again, you see nice and then smooth luminosity evolution towards higher redshift. Why am I talking about luminosity function? I was interested in cosmic star formation history, right? So that's because of this region. So once you have luminosity function, you multiply it with infrared luminosity and then integrate luminosity function. Then you get the cosmic infrared luminosity density, which is related to cosmic star formation rate density through this famous Kennicott relation. So now, by integrating luminosity function, we can do cosmic star formation rate history. So this is the result in cosmic star formation history from redshift 0 to something like a 2 point something, and then this is infrared luminosity density, or in this axis, it's a cosmic star formation rate density. And as you can see, at redshift from redshift 0 to higher redshift, it's gradually going up, and then at redshift 1 or so, it's already density, star formation rate density is already an order higher. And then this is UV. Okay, so compared to the UV, it's this infrared measurement is about an order larger, right? You see it. So this means 90% of the star formation is obscured. So using infrared is very important to do cosmic star formation history. I should also mention this low redshift point. I didn't mention about it. It's from the AKARI's All-Star survey. And then that's also very nicely done by, measured most accurately by our previous postdoc, AJ. This is also recently accepted. So this is cosmic star formation history, all reviewed AKARI. Low G points are from AJ's paper, and then high G points are from my paper. I actually finished, but how much time is remaining? 5 minutes? I still have to talk 5 minutes. Okay, so these other colors are previous work from Spitzer. And you might say, okay, someone might say, oh, okay, it is only confirmed previous work, but I still think it's better to confirm this result. So okay, first our result is consistent with previous result. It's still better to confirm the result with better measurement because we have better acidity fitting, better filter. So I think it's still nice to confirm it. How many minutes do I have?
We can ask questions.
Yes, that'll be great.
Let's thank Tomo first. Questions? Yeah, here.
So why did you choose 12 micron for the luminosity function? Is it special wavelength or just the constraint from the redshift?
Not very special because we have all the filters, so any wavelength we can do. But 12 micron is well studied in the literature. That's why 12 micron, because ISO had 12 micron filter. So people, some previous paper, many of them are 12 micron. So that's the only reason.
So your SED information could contain pH or complicated things. So the interpretation may be complicated.
Okay, so that's another reason. So one wavelength we chose is 8 micron. So that's where pH peaks. And then 12 micron is a little bit away from the PAH, so it's more like a continuum region. So we chose these two wavelengths.
So just following Hiro's question,
Yes.
it looks to me that the luminosity function based on 12 micron is higher compared to other tracers. Is there any explanations for that?
You mean this one?
Yeah, the triangle one.
Okay, this is a very good point. So this is because of the faint ends. So the faint end slope of 12 micron luminosity function is a little bit steeper than other wavelengths. For example, 8 micron or total infrared. That's why this is actually coming up. We suspect our 12 micron is not deep enough to securely capture the faint ends of the luminosity, faint end slope of the luminosity function. So that's why this might be a little bit overestimated. So here I want a little bit deeper data. That would be nice.
Okay, thank you. So if no further questions, oh yes.
Because you only had the mid-infrared observations.
Yes.
So how accurate is your data to do SED for the IR, the total IR?
That's a very good point. So in our local luminosity function paper, in AKARI all-sky survey, we have a fine infrared luminosity for all of the galaxies at low G. So we have assuming that conversion. So that part is okay for low redshift, but we are assuming that relation also holds to the higher redshift.
Okay, we need to move on. Let's say
Thank you very
Tomo
much.
again.